All right, ladies and gentlemen, today's class recording has started, so please refrain from any crude or obnoxious comments. All right, yesterday we finished up our outline about the classification of matter. And so first, all of that classification stuff we talked about over the past couple of days is just based on repeated observations, right? Things we keep observing over and over again, and then within those observations, we look for patterns, okay? First, in order for something to be classified as matter, what does it have to have? Mass and volume, right? It has to have those two things in order to be classified as matter. Then, of all the things that have mass and volume, we broke them up into like two big categories. What were the two big categories that we talked about over the past couple of days? What are the two big categories of matter? Pure substance is one of them, and the other big category was mixtures, right? So pure substances and mixtures. Pure substances have a consistent composition, right? It's always the same thing, no matter where we find it or how big of a sample we have. Mixtures can be, like its name suggests, a mixture of something, but not always the same ratio, not always the same composition, etc., etc. Okay? Good there. All right. What we've noticed, or what we notice and observe about this matter, right, is that even though we may have a pure substance, the properties of that matter can change as we have changes in energy. And as there's significant changes in energy, we move from one state of matter into another state of matter. So the ultimate goal here is to explain, well, why does that happen? And that takes us today, like it says here in the subheading, to the kinetic theory of matter. First, the fact that it's a theory should tell us what? What do theories do for us? Well, they explain why things happen, right? So this is going to try and provide us with an explanation of why do these substances exist as solids or as liquids or as gases. The fact that we call it the kinetic theory should tell you something about what kind of an explanation we're providing. Movement, right? Kinetic energy is the energy of movement. Something's moving, it has the ability to do stuff, right? Kinetic theory is an explanation based on movement. So movement is going to play a big role in what we're doing here, okay? All right. I'm going to jump around in your outline a little bit because, like I said this morning, I didn't like the way the order went. So, all right. In our last whatever, couple outlines ago, I don't remember, right? We talked about our big three states of matter. Okay. Here on Earth, and this is Roman numeral 2 on the front page here. Okay? Here on Earth, we notice that matter exists in basically three states, right? Solid, liquid, or gas. But we also talked about the idea that the conditions here on Earth are pretty unique in that we do have solids, liquids, and gases. We talked about the idea that most of the matter in the universe is in the form of plasma. Do you remember what plasma is from our definition last week, Hannah? It's like pieces, parts of atoms, right? I think hopefully remember that atoms are made of protons, neutrons, and electrons. Yes, right? Okay. Plasma isn't an actual atom, it's just pieces, parts of an atom, right? It's separate protons and neutrons and electrons that just kind of like move around without actually joining together. Most of the matter in the universe shows up in that form, all right? And we said that plasma only occurs at what condition? Where does plasma occur? High temperature, which equates to high levels of what? Energy, right? So plasma exists in conditions where there is high energy. So, I mean, the outline there were more things to fill in, but we already filled them in on the previous outline. So those kind of things are in the previous outline, right? So high energy conditions, we end up with plasma, where we're not talking about like actual atoms, just like pieces, parts. Then Bose-Einstein condensate occurs on the low end of the spectrum, right, where we have very, very low energy. Okay? But because we're dealing with here on Earth, most of our experience deals with solids, liquids, and gases. So why do those things exist as solids, liquids, and gases? And that gets us into our kinetic theory, okay? First, like we said, it's an explanation based on movement. That's the kinetic theory part. The theory states that all matter is made up of tiny particles, which could be atoms or could be molecules, and we'll get into the distinction between those two a little bit later on in the year. But that those particles are moving constantly. Okay? Particles that make up an object are in constant motion. Even something like a solid, where it looks like everything is stable and not changing, there is movement associated with the particles of a solid. Constant motion. What affects how much motion these particles have? Temperature, right? As the temperature increases, the particles move faster. And I think something happened with my wording on there, so it doesn't exactly match up with what's on the board, but you need to know that as the temperature increases, the particles move faster. Also, we've noticed that if we have two substances that have the same temperature, they don't actually move the same speed. It depends on how big the particles are. Bigger particles move a little bit slower than smaller particles, even though they're moving at even though they're at the same temperature. Okay? So same temperature, bigger particles move slower than smaller particles, even though they have the same amount of kinetic energy. Okay? So the theory says that movement determines the state of matter, but there's one more factor, and this will show up as we go on here over the next couple outlines, okay? There's one more factor that affects the state of matter, and that is how much do those particles attract each other, okay? What we find is that, yes, they're moving, but because they're made of protons and electrons, positive charges and negative charges, as they move past each other, they have a little bit of attraction there, like magnets, right? That's similar kind of concept there. So, in addition to the movement, the forces of attraction between those particles will determine the state of matter. So two factors that we have to consider going forward. We have to consider the movement of the particles and the attractions between them in order to help us explain these different states of matter. Those are the two factors we have to keep coming back to. Motion of particles, attraction between them. All right, good? Okay. Here's what I want you to do before we get into the next part. So, some of you teachers use this analogy somewhat frequently. I don't know if the teacher has done this for you, but if we think about coming up with examples to illustrate our different states of matter, okay? If we think about kids at school, part of your school day represents different states of matter, at least in terms of the motion of the particles and how much they are affected by other particles. Okay? So here's what I want you to do before we get started. First, talk to the person next to you, in front of you, behind you, something like that, right? And see if you can come up with a portion of a school day that would represent something that is like a gas, something that is like a liquid, and something that is like a solid. Okay? Discuss. Go.
Yes, so I also think that something that's like a solid in one of those, and I like energy to really tire.
So what part is you guys as the particles of the matter, right? What part of your school day would you represent like something in a solid state? What part of your school day would you represent something as a liquid state of matter? What part of your school day might you represent as a gas state of matter? Okay. So you're the particles that make up the matter. When are you in the solid phase? When are you in the liquid phase? When are you in the gas phase? Okay.
Yes, I
Yeah, plasma, you don't want to be plasma. That's not good.
So you can't really move your leg.
"30 seconds. 30 seconds. Nope. Just be able to answer questions when I ask for them.
hate it.
All right. Let's discuss. So, let's start with our gases. Okay. What did you guys come up with as part of your school day that might represent you guys in the gas phase? You're leaving school. Good, right? Why does leaving school represent something in a gas phase?
Because we're all going in different directions.
Okay, everybody's going in different directions and dispersing, right? What else could leaving school, how else could leaving school represent something in the gas phase?
We're all like high energy because we want to go home.
Good, lots of high energy, right? Okay, what else are you guys doing? Spreading out, right? Farther apart, right? More room to operate in, okay? That's pretty good, okay? The other example, and you guys unfortunately don't get to do this anymore, but another good example of something like that would represent gas phase would be like recess, right? Okay? I know, the good old days. Although I am a pretty firm believer that you guys should have like a recess book. You guys really should have like even just like 20 minutes where you don't playground. So you don't even need a playground. You know what? Just like go sit like in the gym or shoot some hoops for a little while or walk around the track. Or,
Average unit dance 45 minutes, but we have like a 7-8 hour school.
I know. So, or even if we don't have recess, even if like time in between classes maybe was a little longer, like maybe it's like 10 minutes in between classes. Yes, Isabel. Okay. So, Isabella brings up a good point. That on recess, what do kids tend to do somewhat? Yes, move around, but if you're playing with your friends, sometimes you kind of like clump together. It's not a perfect analogy, all right? But do you understand how that kids at recess have high energy? Maybe you're, not maybe, usually you're spread out more than you are like in other parts of the school day, and those are the important parts as far as gas goes, okay? All right, so, behavior of gases. Particles of a gas are in constant random motion at very high speeds. If we have constant random motion at very high speeds, what does that tell you about the energy of the particles? High energy. And we said high energy corresponds to what? High temperatures. Okay? So gases generally exist at higher temperatures. Constant random motion, high speeds. Gases have more energy than liquids or solids of the same material. Whatever the copy center sends back to me. Whatever the copy center sends back to me. So.
No one listens.
All right. If gases have more energy than solids or liquids of the same material, what does that mean they're capable of? Doing more stuff, right? That's energy. You ever been cooking something on the stove and you have a cover on something and you lift the cover big steam like comes up at you, right? That hurts sometimes, especially like if you get, like your hand caught on the side, something like that. Those gas particles have a lot of energy. They have a lot of ability to do damage, right? And pretty quickly, because they have that high energy, okay? All right, what else about gases? The motion of one particle is not affected by the other particles. We said that going back to the kinetic theory, we have to consider two factors in determining the state of matter. What are the two factors that we have to consider? No, that makes something, mass and volume makes something matter, but when we talk about the state of matter, right, two things.
Temperature.
Which is,
Energy.
temperature tells us about motion, right? And then what else do we have to consider? The motion of the particles, the attraction of the particles, okay? If the motion of one particle is not affected by the other particles, what is that telling you about the attraction between them? Are they attracted to each other?
No.
No. Why aren't the particles of a gas attracted to each other? Yes, why? They're so fast, and what else are they?
Really hot. Expanding.
They're very far apart, right? Okay. The attraction between the individual particles is so small that it pretty much can be ignored. If we go back to the recess example, right? If we go back to like a recess example, if you were the kid on recess that just wanted to spin around in a circle for a half an hour continuously, could you do that?
Yeah.
Yeah, right? Perfectly fine. Now, because the particles move so fast, and because they don't really affect each other, it allows our gases to basically fill up whatever container we put them in.
Like the atmosphere.
Like that, or like the atmosphere. Now the atmosphere actually, right? The atmosphere actually doesn't have a container, right? Like there's no like glass cover to keep all the atmosphere, right? What keeps our atmosphere on our Earth?
Gravity.
Gravity.
Another question.
Right?
Does gravity affect gases?
Yes, because gases have what? Mass and volume, right?
They have
The,
density.
the mass is important. That's the important part for gravity. We'll get into gravity a little bit later on.
But it's like less than a solid.
Say again?
How does it less?
Because they move pretty fast. So sometimes we can overcome that gravity, but not fully. Yeah, does that make sense? Okay. But it's also why as we go to higher altitudes, like if you go to Denver or something like that, the atmosphere is thinner because gravity pulls more of the atmosphere closer to the surface, and that's why the air is thin because it's farther away. Gravity has lesser effect on it. All right, so gases, no defined shape, no defined volume. They will go and basically fill up any container that we put them in. Okay? Good?
Excellent.
All right. Liquids. What part of your school day would you be representative of the particles of a liquid?
When we're in the hallway.
When you're in the hallway. Hallway is a great example of particles as a liquid. Can you move through the hallway?
Not really. Well, let's be honest.
You can,
I sat
right?
behind a girl who was
But-
on the phone and wouldn't see that.
But, so that's a good example of but. Can you move through the hallway? Yes. But are you free to move however you want to in the hallway?
I wish,
No.
but no.
There's a lot more interaction between the particles that make up a substance in the liquid phase. Okay? Particles of a liquid move more slowly than gases and are more closely packed together. Right? We said gases are very, very far apart and move very, very quickly. Liquids don't move as much and aren't as far apart. And that means that the particles of a liquid will have less energy than the particles of the gas, but more than solids. Good there? Okay. Because those particles in the liquid are closer together, now that other factor starts becoming more significant. We said that gases move so fast and are so far apart that they almost have no attraction for each other. But when we slow down the particles, like we do in the liquid, and bring them closer together, now the attractive forces become more significant. It allows those particles in the liquid to sort of hold on to each other. That means, right, that particles can still move, but just not as fast as they do in gases. Okay? We said that what happens when we put a gas in a closed container? It completely fills that container. All the nooks and crannies, all the space, completely spreads out. Will liquids completely fill any container that you put them in? No. There is some movement, right? If I take the water that's in my water bottle and I pour it into a water bottle of a different shape, it won't fill that container up, but it will take the shape of whatever part of the container that it's in, right? So it's got a little bit of freedom, but not total freedom, right? Mixing occurs more slowly in liquids, and that ends up with the fact that we have no definite shape, right? But we have a definite volume. And those are the two key characteristics of matter in a liquid phase. We have no definite shape, right? It'll take the container that we have, shape of the container, or whatever part of the container it fills up, but it does have a definite volume. Particles can't just go wherever they want to and completely fill the space that they're in. Okay. All right, good there? So gases have no definite shape and no definite volume. They'll just completely fill up whatever container we put them in. Liquids, they can mold their shape a little bit, but they won't completely spread out. Okay? And that brings us to solids, right? What do we know about a solid something? What about the shape of a solid? Does it change? Nope. Well, let's go with that. Solid won't change its shape. What else won't it change? It won't change its size, right? It's a definite size or a definite volume. What part of your school day representative of a solid? Kids in the classroom, right? Is there no motion when you're in the classroom?
There's barely.
Can you move while you're in the classroom?
Slightly.
Yeah, right? All of you are moving right now, okay? Can you move from the spot that you're in?
Yes, kind of.
I mean, yeah.
Okay, just put something else, so.
All right, true. All right. Particles of a solid basically vibrate. Twist, turn, vibrate, right? But they're kind of stuck in one location. The movement of the particles is very slow. What does that mean about the forces of attraction between those particles?
They're attracted on.
Pretty strong, right? And that keeps them all in a fixed location, right? Solids have the least amount of energy of all of our states of matter. The particles that make up a solid have the least amount of energy of all of our states of matter. The three that we deal with most often. Theory, yes. Reality in like very extreme conditions. Nothing here on Earth. So.
Why didn't even after Einstein?
Einstein has his hands in a lot of different things, and so some of the theories that he put out there do explain why these substances behave in the manner that they do. Even though we kind of think of Einstein as like a physicist, like, yeah, I mean, there's MC squared and that kind of stuff, but there's kind of application abbreviations.
Well, I think, I don't know what E stands for.
Yeah, what does that equation?
E stands for energy,
Mass volume.
M stands for mass, and C stands for the
C.
speed of light. So we will actually talk about that a little bit later on.
Well, yeah, why is it square?
That's weird. Yeah. Exactly.
Einstein said quadratic.
So,
Yes, it's
so
quadratic. Yeah.
if you graphed it, yes, it would be. Well, then you can just look at the equation and see that it's squared. It's quadratic. Although what we learned is that the two variables in that equation actually are E and M, and C is a constant. So the relationship between E and M is actually a direct relationship. So, all right, good. Particles of the solid are really strongly attracted to each other. They move much less. It prevents them from being able to move away from each other and do whatever they want to. That means that solids end up with a definite shape and a definite volume. Okay? Good? Congratulations, everybody. We took 1 day to do an outline. That's it. Like a whole outline in 1 day. All right? All right. Before I turn you loose, a couple things I want you to look at. And I'll put them up here on the board. Okay. So, quiz over this outline and the previous outline is due on Friday. You now have all of the information that you need in order to do that quiz. However, if you need to reinforce some of the ideas that we talked about over the past couple of days, there are 2 reading assignments on the calendar. Section 2.1 talks about classifying matter, pure substances, mixtures, heterogeneous, homogeneous, elements, compounds. Section 3.1 talks about solids, liquids, and gases. Those reading assignments from the book reinforce what we do in class. So if you're not quite sure, or if you're looking for a way to review some things when you're at home, taking a look at those sections of the book would be a good idea. Even if it's just to look at the bold-faced words and the headings, the section headings and that kind of stuff. Okay? Also, there are some questions on here that reinforce the concept that we went into today, like, what's a solid, what's a liquid, what's a gas, how do we, different motion of the particles and that kind of stuff. Okay? So if you're looking for ways to review either before or while you're taking your quiz, you have resources there outside of your outlines. Okay? Good? All right. I will see you all tomorrow.